So good afternoon and welcome to this new Epic online technology meeting. This time we are going to talk about specialty optical fibers for lasers. It's 3 p.m., so it's time to start. My name is Antonio Castello. I'm technology manager at Epic in charge of all the laser topics and also biomedical applications. And it's a pleasure to welcome you to this discussion where we will talk about the different proposals from manufacturers about new materials, new shapes, new possibilities in terms of optical fibers, and also the point of view of the industry about what solutions are using nowadays, and also needs and challenges for the future. So I'm hope you will enjoy the discussion you will have. And before we start, this is Epic. In case somebody doesn't know, we are an association of more than 800 companies related with photonics technologies. We cover topics, a very big variety of topics from lasers to quantum, photonic integrated circuits, semiconductors, imaging, all the related possibilities can be inside Epic. And we have here a small summary of all the benefits. So, of course, we support our members with their technological needs in case they want to explore new possibilities, in terms new partners for a solution, new alternatives for certain components, etc. We have also offer market reports, access to market reports developed by different partners. Also access to markets. We support with human resources activities. We have also a list of investors and venture capital companies we can put in connection with our members for the ones that are interested in exploring these possibilities. And of course, we have networking activities like the one we have today, putting in the same room or in the same online room all the people relevant for the one certain topic, today specialty fibers for lasers, and discuss about what is needed in the future, potential collaborations, and find also business opportunities. So any question or any comment, any need, please feel free to reach me. You have here our email addresses, so do not hesitate to send me an email with any other idea that you can have in mind. About networking, a short summary of the Epic events. I, of course, encourage you to go to our website to check what is happening next. But we have a good set of events during the whole 2026 year. These are the closest one now. In terms of physical meetings, we will have, in fact, this week, a meeting on integrated photonics in Netherlands. We will visit France in March to talk about photonics for defense, and then we will be present on one side in OFC in the United States. So I guess some of you will be there as you are involved in the optical fibers and probably also interested in datacom, telecom. So this is the show you will probably attend. So some of my colleagues will be there, and we will have some activities there. And then we will also be present in the W3 Fair in Germany, and we will also have some activities there. So, as I mentioned, go to our website and check the ones that could be interesting for you to improve your networking activities there. And of course, we will have online meetings again, combining technology meetings like the one that we have today, also technological reports and online marketing meetings, and to highlight the one that we will have tomorrow, that is probably also interesting for some of you. We have this technological report only available for Epic members, a report developed by Thematis, and is going to be in ultrafast lasers, technologies, applications, and markets. They will have a document available for the Epic members soon in our website, and tomorrow is the opportunity of having a short summary, short presentation by the person in charge of the preparation of this document, so you can exchange also with him, see what's included in the document, in the report, and perhaps make some questions or share some ideas also for the future. And regarding the topic for today, and more in the long term, to meetings that could be interesting for you. The first one is related with laser microprocessing. So we are talking today about fiber for lasers. A lot of ultrafast lasers and standard lasers are related with fiber. So could be interesting for you to travel to France to participate in this meeting related with microprocessing in Bordeaux, Pessac. We will also visit different members in the area, different companies in the area. And on the other hand, more in the fiber side, we will be visiting Arbus facilities in Hamburg. So we are going to have there a technology meeting on optical fiber sensing. A little bit more general in terms of the discussion, but of course, it will be a little bit focused on aerospace applications. So both of these meetings are in the website already. As I mentioned, feel free to go to the website, check what is in the agenda, and also feel free to come back to me if you have any idea or interest in any of them. And let's go now with the agenda for today. This is all the companies that we have registered for the meeting. So I'm happy to see a lot of interest in the discussion about specialty fibers for lasers. So we have a good combination of companies that are developing laser itself and also machines based in laser sources. Also the development of components and modules, not only optical fiber, but also other components for application in lasers. Of course, materials, that is very important for fabrication of fibers, and then a good combination of R&D companies and centers, also distribution, metrology, and testing. So you have here this map of companies that are registered for this meeting, and this is a slide that we will also upload to the website of this meeting later on, so you can check all the people that was interested before in this meeting. And regarding the agenda, as I mentioned, we have a good combination of companies that are manufacturing fibers for lasers, companies that will share some ideas and some point of view about the use of the fibers for laser itself. So we will have a different point of view, and I'm sure it's going to be interested. So we have presentations by Lightera, Glow Photonics, Bluetooth technologies, Amplitude laser, Fluence technologies, R Photonics, and Excel as well. And we can go with the first presentation. We will have time after each presentation for Q&A. So I encourage you to raise your hand. That is, there is a button available for making your questions to the speakers, or use also the chat if you cannot open your mic and write your question directly to the speaker. But we want to encourage you to have a interactive discussion. So we are more than happy if we see some questions arising after each presentation. As I mentioned, we can go now with the first speaker. So it's a pleasure to have here Simona Opter. She is R&D glass and coating manager at the company Lightera. That is the branding that appeared last year with Furukawa and OFS former companies. So it's a pleasure to have Simona here, and she's going to talk about their specialty optical fiber for high power laser applications. So Simona, I'm going to
Hi.
stop sharing, and you can share your screen. Thank you for being here today.
Thank you for inviting me to present this. So can you hear me?
Yeah, we can hear you.
And can you see my screen now?
Now is working. Thank you very much.
Okay, thank you. So yes, thank you for presenting me. So I am coming from Lightera, and I will talk about specialty optical fibers for high power applications. As you mentioned, Lightera is a very new company by the name. So we started 1st of April last year, where a few larger units of Furukawa and OFS were joined together under the new name. So I come from the part of OFS, formerly known OFS. In site of Lightera, we have a specialty solution division, which is located at four locations. And one of them is Brøndby, Denmark, very close to Copenhagen, where I'm sitting. So what we do in Brøndby, Denmark, we have a long history of producing optical fibers for different applications. All optical fibers are silica-based. So we have large-scale production of transmission fibers for terrestrial, for oceans, for easy band solutions. And we also have large production facilities for specialty fibers. So our erbium doped fiber, ytterbium doped fiber, polarization maintaining fiber, coupler fiber, many different ones. Besides production facility, we also have R&D facilities in Denmark looking into future fibers and next generation of current fibers. So generally, what we have in Lightera on ytterbium doped fibers, it's a quite broad product portfolio. So we have fibers with various core sizes from 6 to 300 micrometer and also cladding up to 500 micrometers. We do dual clad fibers, triple clad fibers. We also make ytterbium doped fibers with polarization maintaining properties. Because of this broad product portfolio, I selected three different products or merging products that I would like to present today. So they are all based on cladding diameter of 400 micrometers. They are for different power levels, if you can see in this table, and they are also for different applications. So the last one in the table is polarization maintaining one with for pulse applications. So if we start with the first one, which is True Lace YB22400. It's developed for pump at 915 nanometers, and its application is 3 kilowatt fiber laser. We, besides developing and producing, we also have small or some testing facilities for fibers at high power in-house. So in our test setup, this fiber was tested with co-pump amplification configuration, and it reached 3.5 kilowatt, which was actually limited by available pump that we have for the test. And under this, it's shown in the graph below, under this operation, we didn't see any transversal mode instabilities, and also fiber is photodarkening free fiber. So the second fiber that I want to mention is for multi-kilowatt class fiber lasers. So we again tested the fiber in our test setup, and we could reach 5.2 kilowatts, again with limited by available pump power, and with high in stable operation. Also, we run tests under 2 kilowatts to see any photo darkening, and we have photo darkening free fiber. And from the same fiber, we also have standard product available. And by slightly changing thermo-optical coefficient of the new fiber, we could increase the performance drastically from standard to decrease TOC, as you can see in the table. So, and the third fiber that I want to mention is its polarization maintaining version of the fiber with for ultrafast pulse laser application, like for micro machining or glass cutting. And that fiber has a large core area, and it has high cladding absorption. So it's designed for operating in this pulse regime, especially by optimizing the higher order mode suppression. So we tested also in our setup. More is written in the cited article below how the test setup looked like, but we could achieve 1 millijoule pulse energy with a peak power of 150 kilowatt by having low m square of 1.1. Yes. So to make sure that all this fiber can operate on the long term and at this high power, where it also generates high increase of the temperature in the core, we look into also stability of the coating at this high conditions, high power conditions, and we know that the glass host will be sufficient stable when operating the lasers with active cooling and so on, but coating needs to be stable also under that condition. So recently a new procedure was developed in Lightera how to do the lifetime prediction for polymer coatings, and we use this one also for our low refractive index coatings. And we can see that if you plan to operate fiber for 20,000 hours, then the temperature at which you operate should stay below 115 degrees centigrade. And we tested this also by following the properties of fiber and coating. And here it's just one example of a refractive index after this change of weight for 10%, it stays the same. So it means that properties of coating should remain. So, and now fast summary. So we are Lightera, which our specialty solution comes from former OFS. We have very broad portfolio of YB doped optical fibers. And I showed three examples. One is true is YB22400 for 915 pump, which it's TMI free up to 3.5 kilowatt. And we have a new version of LMA, YB LMA 2400, which is TMI free up to 5.2 kilowatt. And we also have PM version that can achieve pulse energy up to 1 millijoule with low M square. And all these fibers have a low refractive index coating on that is stable for these high power applications. So thank you for listening. And any questions I can answer.
Thank you very much, Simona. So we have time for questions or comments. So as I mentioned, you can raise your hand, also use the box for questions. Yeah, we have a question from Andrei from Ceramutech. So Andrei, you are muted right now.
Yeah, hello. When you are talking about high temperature and low index coating, are you talking about silicone type coating or acrylate type coating?
For our fiber, we have at the moment acrylate type of coating.
High temperature acrylate with a low index.
Yes.
Thank you.
Thank you, Andres. Any other question or comment? Perhaps I have a more general question, because we see now more lasers going into really high power, so tens of kilowatts, 20 kilowatts. So how's the approach of Lightera? Do you also plan at some point to offer solutions for this kind of extreme high power lasers? For the moment, you will keep your offering in this level of powers, or what's the proposal of Lightera for these solutions?
So yeah, we have done a bit on power scaling. Of course, the fiber that I show goes to our pump limit. So I assume we need to update our test facilities to see how far we can go. And yeah, we are looking into now more also European markets, since some of the fiber is produced in Europe and for high power application.
Mm-hmm. Okay. And regarding the coatings that you mentioned, did you also explore different solutions of compositions for the coating, or do you have more or less clear what was the material that you need to use to compensate these thermal issues, potential thermal issues?
I think the current coating, it works okay for the current applications, but of course, if it goes to higher temperatures, operating temperature, we are looking into other coatings also.
Okay, very good. I don't know if there is any other question or comment. So if not, we thank Simona for being here today. And Simona, perhaps you can write in the chat your email address in case somebody wants to reach you outside after the meeting, so you can then discuss further with this person.
Okay,
And thank you for being here today. And we can now move to our next speaker. So it's a pleasure to have here Jan Sabosh-Vicen, the CEO of the company Glow Photonics. Glow Photonics is, I think, quite well known for the expertise in hollow core fibers, and he's going to present today the innovative fibers beam delivery solutions for ultra short pulse lasers. So Jan, the floor is yours.
Thank you, Antonio. Can you see my screen?
It's still loading, but now we see. Thank you very much.
Okay, perfect. Thank you so much. Thank you for the presentation. So I'm Jean Sauvage Vincent, and today I will deal with hollow fiber, and I will make a focus on beam delivery application. Yep, sorry. Okay, Go Photonics. We are a company based in Limoges, so in France, in the beautiful city of Limoges, 15 employees. We do have a drawing power. It means that we can make our own hollow fiber, specialty fiber on site in Limoges, any type of fiber, but only hollow fiber. We're not dealing with other type of fiber. So we are purely focused on this activity. What we can address in terms of different markets, of course, beam delivery application, the one we are going to discuss today, but also we can address some application like frequency conversion, pulse compression, because with the hollow fiber, you can fill the fiber with gas, and so you can have some interaction between light and gas in the hollow fiber. And other application is quantum technology. You can fill the fiber with gas and with some component, molecule, and so on, and you can address very different application and market. But today, I will just focus on beam delivery application on high power laser and mainly USP laser, so ultra short pulse laser application. So one of the things we want to do with the hollow fiber is to bring light from a point A to a point B, and this light is ultra short pulse laser. So one of the problems with the standard fiber we can solve with hollow fiber is nonlinearity first, as you overlap with the silica cladding. Silica, in fact, because silica is a limitation if you want to bring light from a point A to a point B. And with the hollow fibers, the overlap with the silica cladding is so small, then you can now guide the ultra short pulse laser from point A to a point B. So we can solve this with the hollow fiber, and we have built a complete system around the hollow fiber, so to manage the guides inside the hollow fiber, so to be in the vacuum environment, and to deal with thermal load at the tip of the fiber as well. And so we can offer different type of components depending of power, energy of ultra short pulse laser, starting from very low power, low energy laser with what we call the patch cord. It's a simple piece of fiber with standard connector. And then we can go to a complex integrated solution with vacuum connecting to the fiber, dealing with the thermal, etc., etc. And we will make a focus on what we call the BDS HP STB PM. Sorry for the name, but it's a hollow fiber system, which is a PM, so polarization maintaining system, which is quite new in terms of, let's say, option for the hollow fiber. So what we want to promote here, it's hollow fiber which can bring 100 of microjoule, 60 watts, almost 85% transmission with a PER, polarization extinction ratio, of 18 dB. Okay, so it means it's quite good, let's say, in terms of polarization, even if you will move the fiber, and I will show you that in the next slide. So just to give you a bit of information of the hollow fiber, one of the things with the hollow fiber is the NA of the hollow fiber is very small, 0.02, which can be interesting, but also it's a problem because it means that injecting into this fiber, it's difficult. It's difficult, and if the laser is moving around the fiber, you can damage the hollow fiber. And so what we have seen at Go Photonics is that the depointing of the laser of more than 5 microrad means that you will have more overlap with the silica cladding, and you will start to damage the hollow fiber, as you can see on this slide. So it's a limitation, it's plus minus 5 micron at the tip of the fiber. And here we have implemented a beam stabilization in the system, so to stabilize the beam at the tip of the fiber, to transform this variation of movement of the laser, so a strong variation from minus 20 micron to 15 micron, so more than 30 to 40 micron beam depointing at the tip of the fiber, into 5 micron beam depointing. So now the laser we have in front of the hollow fiber is good enough in order to be injected into the hollow fiber. And so you can have a very good transmission, beam quality at the output of the fiber at different power, energy, etc. So what we show here is 150 continuous wave laser. Yes, 150 watts, continuous wave laser, very stable all the time. And the same with the ultra short pulse laser, 300 femtosecond, 40 watts, 100 of kilohertz. So what we demonstrate here, you can inject properly into the hollow fiber, high power, high energy laser, continuous wave laser, or pulse laser, ultra short pulse laser. That's the first thing. It means that with the hollow fiber, you can address this type of market at in the infrared part of the spectrum. Now we want to have a hollow fiber, a system made of hollow fiber, which can bring light from a point A to a point B, but to be PM, so to have a polarization, linear polarization at the output of the fiber. And one thing to mention is with the hollow fiber, you cannot usually have a linear polarization at the input, which remain linear at the outputs, and moving the fiber will change this linear polarization that will rotate according to the movements. So here we have developed at Photonics a solution to keep the polarization stable, even if you will move the fiber during the process. So what I will show in the next slide is the result of the polarization. We will look at the polarization, and we are moving the fiber, torsion and bending of the fiber. Okay, and what we have seen is that the polarization at different power and energy will remain stable over time and will stay the same even if you are bending or applying a torsion to the fiber. One thing we can see here, the torsion is more aggressive, let's say, in a way, because that will have an impact on the polarization, which is more important than the bending. But usually in the application, bending will be what you will be in front of instead of the torsion. Okay, and just to show you, oh, sorry, there is a video. Let me see, yes. So here you have hollow fiber, which is mounted on a robotic arm. We are moving this fiber in front of a camera. We are looking at the beam quality, okay? And we are looking at the variation of the power by moving the fiber. So polarization is good. We are in the range of 15 to 16 dB. And we are looking at the variation of power when moving the fiber around. And what we can see here, when moving the fiber, we keep a good power over the movements. So I'm not sure I will let the video go to the end, but you can see you can move the fiber and you can still have a good power and a good beam quality at the output of the fiber. It's a femtosecond laser, just 2 watts. The next step for us is to demonstrate a 40 watt as well. So polarization, power, and energy. You can do everything with the local fiber. And just to promote polarization on this robotic arm, we use the local fiber. It's PM, we have power, we have energy. And just to be sure we have a good polarization, we have done this performance with the guys of Amplitude and Alpha to engrave some ripples. Some ripples, it's a very specific structure. You can engrave on a metallic surface, and it's very dependent on polarization. It means that if you can engrave ripples, it means you have a good polarization. And it's exactly what we have shown, what we are showing here. We can engrave some ripples on metallic pieces. So it means we have a good polarization, good power, good energy, and the beam profile remain good in order to make a good engraving. So all the type of system we can do, because we can make power, energy, polarization, but if you have any interest in splitting the power, the energy, because the laser is increasing in terms of power, energy, and we can split them, so we can offer different type of system like beam splitting into the hollow fiber. We can offer any type of bundle of hollow fiber as well. And I want to finish on this one. I mentioned power, energy, a femtosecond laser, high power, high energy in the infrared polarization. But now we are moving in the UV part of the spectrum as well, because we can offer also 343, 355, even 266, 213 nanometer hollow fiber to address different type of markets. And I think I will stop here just to remind you a bit of the different parameters I've shown previously. I don't want to bother you too much with this number, but do not hesitate to send me an email, and I will be pleased to answer. And if you have any interest in the local fiber, please let me know. Thank you so much for your attention.
Thank you very much, Jan. So we again have time for questions or comments.
Yeah, please.
But perhaps initial stupid question, but when going to the UV means that you are using different materials for the fibers, or is a
No,
different
still,
shape in the...
no, still solarization. I think I get your point with the solarization or photodactyl. There is two things. With the local fibers, the overlap with the silica cladding is very, very low. So you will not have too much interaction with the silica. Second point, we are treating the silica in order to prevent any photodactyling or solarization as well.
Okay. Okay, so it's kind of similar fiber, but with a special treatment to go into more UV wavelengths. Yeah. Very good.
True.
Good. Any other question or comment? Yeah, Andres again.
Jean, when you are moving to, say, lower than 400 nanometers, then you need to make very thin silica walls in your capillaries. Approximately half of the wavelengths, yeah. In your fibers, you're using the same principle or some other smarter arrangement of, say, of these anti-resonance structures?
We are not very smart. We are using the same physical mechanism. One thing is very interesting is, in fact, you are not only limited by the thickness of the wall, because in the hollow fiber and tyrosine fiber, you will have multiple transmission band. Okay, so what you said is that if you want 400 nanometer, you will be in the region of the 200 nanometer wall thickness. It is true, but in the meantime, you can also have a thicker wall thickness, but the transmission band in the UV will be smaller. So it will be more difficult to be well centered into this transmission band. So yes, it's better to have a ratio of, let's say, 400 nanometer will be 200 nanometer wall thickness. But in fact, there is some trick in order to have a thicker wall thickness and to still have some good UV transmission.
Thank you.
My pleasure, Andres.
Any other question for Jan? Perhaps, Jan, we can finish your experience with EPIC question. So we always ask, what can you do for the others? What can the others do for you? If you can summarize something that other companies can do for Photonics.
Yeah, true. You're right, because it was was promoting my product to be transparent with you. But you're right. I do have some requests to other guys from EPIC. Difficulty for Glow Photonics, there is one big difficulty, is we don't have all the laser. And what I'm saying here is that we can do UV, we can do infrared, we can do mid-infrared, etc. But we don't have all the means to test this fiber. So we are super open for collaboration. So to test the fiber and to build collaboration for UV application, any type of application, we are very open, because we have this hollow fiber. We know we can do plenty of things, but you guys will be the driving force. So we need you in order to test a hollow fiber and to find some new solution. So very open to discuss with any laser manufacturer, laser integrator, to see what we can do together.
Very good. If there is no question, you can perhaps, Jan, put your email address in the chat, and somebody interested could then reach you afterwards, or anybody interested can reach me also, and we can put you in contact with the Glow Photonic directly.
Thank you.
So thank you very much, Jan. Thank you for the presentation today.
Thank you.
So we can move now to our next speaker. So we have Samir Lamrini. He's founder and managing director of the company Bluetooth Technology. Bluetooth is quite a new company, founded to propose this UV LED curing solution. So we have a presentation about how this solution can be used for the optical fiber, applied to the optical fiber industry. So Samir, thank you very much for being here, and please feel free to share your presentation and your ideas with all of us.
Yeah, hello everybody. Antonio, thank you very much for the introduction. So my name is Samir Lamrini, and today I would like to present our UV LED curing system. which has been developed and designed for the specialty fiber industry. So this is our mission and vision. We provide UV LED systems, and our, let's say, promise is that we can unlock the curing of any optical fiber coating. So we are located in Germany, quite in the center in Germany, in Göttingen. And my core team consists of PhD student who is doing the basic research, UV spectroscopy, for example, and some senior engineers. And we look back at the total experience in deep tech and photonics exceeding 95 years. And switching now from, let's say, the lasers to some specialty applications which are highly regulated. For example, in space communication, as you know, they have some specific requirements, not only for the glass but also for the coating. So the focus of this presentation is more on the coatings. As you can see here, we have also applications for medical or surgical lasers. We do have optical neural networks, and the message behind this is shown in this slide. So the core message here is special environments need, of course, special fibers, and these again need special coatings. And here you can see some examples of special geometries here, for example, from Weinert Industries, or also multi-core fibers by Exail. You see here a lot of different geometries, so a broad range of, let's say, possibilities that you can manufacture. But the core question is, can any design be fabricated? Yeah, and this was also one of our core questions when we started the development. What we experienced is that the clear answer is no, because in most cases, the coating cannot be fully cured. And this again affects your application. If you have this sticky coating, for example, it can either introduce high optical losses or doesn't meet the optomechanical, let's say, requirements. So this is why we are introducing this novelty to the market. On the left-hand side, you see the historic background. So Heraeus launched the first UV LED curing system. You can find the systems by Optogear, Optolite, Phosion, etc. But let me focus, or let me underline, that these systems, they just replaced the mercury lamps. So there was no fundamental, let's say, optical design improvements or machine learning or any process intelligence. And here is where we step in. Yeah, you can see here in the left, on the left-hand side at the bottom, what we achieved. Yeah, we do have 2 times the lifetime, which reduces your capex in your manufacturing capability. We do have 2.4 times the energy efficiency. This again reduces your OPEX. And we also have reduced the inert gas consumption. You know, gases, the inert gas, nitrogen or argon, for example, they are very expensive. You can save 90%. So this again will also reduce your OPEX. And one highlight of our system is that we can also cure high temperature coatings, which are very, very interesting for kilowatt power levels, lasers, etc. And on the right-hand side, you see the benchmark, between Blue Tube and, let's say, the state of the art. Yeah, and here we do have some special features that enable the curing of any coating. For example, we do have the wavelength mixing, because some specialty coating materials, they have a kind of broad absorption bandwidth. So here we can match our curing lamp to this absorption spectra. We do have also the adjustment-free and maintenance-free feature. So that means we do not have any optics in our system. So there are no lenses. We do not have let's say a line. We do use the primary radiation of the UV LEDs. And also, this will also be shown in one of the next slides. We do have separate curing zones and intensity tailoring. And this means that you can also adapt your system to the let's say material what you are curing. For example, soft glass materials or silica, etc. Here you can see the devices. You have, for example, one cluster for the primary coating, the second one for the secondary coating. You have here a 19-inch housing, for example, you can control via touch screen. But the more interesting is shown here. We defined, and this is also patented, by the way, we defined the curing zones, yeah, in any of the used clusters. So we have, for example, on the left-hand side, the top is zone 1, the bottom is zone 2. And the customer selects between the wavelength tailoring, the intensity tailoring, and our unique curing dynamics, yeah. This is what I will show you on the next slides, allow us to cure, let's say, also very, very complex coating structures, yeah, with very, very high curing levels. And here in the center, you see the screen. You have the first zone, the second zone, and you can independently adjust the power of the different zones. And on top, you are also able to mix these wavelengths that are listed here, 365, 385, 395, and 405. So here I'm giving you some examples. This is the shock curing mode. For example, the zone 1 is at maximum, and this is suitable for very thick coating layers with low concentration of photoabsorbers. So we'll need a high intensity, and the second zone is then responsible or enables deep curing, yeah, the full curing of the material. We do also have the vice versa. So this is soft curing mode. So at the initial point when the fiber passes here, yeah, you can set a very, very low intensity. This is, by the way, very interesting for low temperature fibers like fluoride fibers and so on. And then here again, you can set the curing zone power of the second one to a higher level in order to achieve deep curing. And for standard coatings, yeah, we have uniform curing modes, so you can set both zones to 100%. And here you can also use them for thick and thin coating layers and for very, very high drawing speeds. So for all curing modes, you still have the opportunity, or you always have the opportunity to do the wavelength mixing. Yeah, and this was also one key why we were able to cure the high temperature coatings. So this again is just an overview. I will not go through all the points, but here are some of the coatings that we were able to cure with a very, very high, let's say, curing level. And as you can see, we do have recoating materials, and we also have coating materials as primary and secondary coating. And this one, it's a coating, it's a high temperature coating fabricated by Koya. It goes up to 250 degrees. And here we also achieved very, very high curing levels. The other message here is that we do have demo units available with ultra short lead times. So if someone is interested, we are very, very happy to install some demo units and to discover new opportunities. Here are some pictures. Yeah, it's mounted to a fiber drawing tower. Yeah, this was the first cluster. Then the fiber passes here, and this sliding mechanism, so to speak, is also adjustment-free and maintenance-free. So these are the take-home message. So we presented the world's first high-power UV LED system, which can unlock, or which unlocks the high drawing speeds for specialty fiber coatings. Regarding the power and gas consumption, we are ready to meet the Minamata Convention, so it will definitely come, based on the convention regulatory. Of course, we do have patented operation modes, and also the software, some software features are also patented. And as I mentioned, this system has been developed, backed by intense R&D work, and demonstrates industrial grade performance. And this is what I already mentioned. So we are happy to discuss with you the opportunity for tests and demo units. So this brings me to the last question and answer. Now we can say definitely, yes, we are able to do or to cure any coating. Thank you.
Thank you very much, Samir. So again, we have time for questions. So Simona.
Yes, so you mentioned hydro speed. Can you give any number to what kind of hydro speed you're looking at? And can this be scaled up by longer curing length or?
Yeah, with a single system, we will be able to draw speeds between 120 and 150 meters per minute.
And this can be scaled up or?
Yeah, because one driver can drive, let's say, 2 clusters. And we also did some experiments. Of course, it's not 100% linear because the absorption is also not linear, which you may know. But you can definitely, there is a big potential to scale, to further scale.
Okay, thank you.
You're welcome.
More questions for Samir? Yeah, Robert. You're muted
I
right
don't
now.
hear you.
You need to unmute this on the left down. You will see the microphone, audio microphone.
Me. Oh, okay.
Now we
I
hear
have
you.
it. Good. Thank you. Thanks for the nice talk. Is there a limitation on the diameter, fiber diameter?
No, we are flexible in the, let's say, in the hole where the fiber passes. Currently, we do have, let's say, a hole of 4 millimeters. So I think if you draw very thick fibers, it's also possible, but we can go also up to 6 or 7 millimeters in diameter.
Okay, thank you.
You're welcome.
Any other question for Samir? I don't know if you mentioned Samir, but what about the polymer fibers? Is something that you could also look at, or for the moment would be more in the glass?
No, there are some let's say results in our data bank, and compared to other systems, we are also able to have a very gentle adjustment of the power. So you can really use 1% steps. And as you may know, these polymer fibers are very sensitive to temperature.
Mm-hmm.
If you just exceed, let's say, a bit of the temperature, then it's more or less useless. So we do have data on file for very low, let's say, intensities for POFs.
Okay, good to know. We have time for one final question for Samir. Well, if not, thank you again for the presentation today. And as I said to Jan and Simona, you can perhaps use the chat box and write your email address, and people can reach you afterwards. So thank you for being
You're
here
welcome.
today.
Thank you very much. Thank you a lot. Thanks a lot.
Thank you, Samir. So we can move now to our next speaker. So it's a pleasure to have here Miguel Melo. He's the manager, director of the company Amplitude Laser Portugal. So Miguel is the founder of the former MW Tech. So he has a long expertise in the development of laser sources based on fibers. And now MW Tech is part of the Amplitude Laser Group. So Miguel, the floor is yours.
Thank you very much, Antonio. I'll just share my presentation.
Yeah.
Okay.
Yeah,
so,
now it's in full screen. Good.
Okay, perfect. So first of all, thank you very much for the opportunity to present after a very long time something in this type of meetings. It's always good to be with you and with EPIC. So as a challenge that you made me, I decided that I should position myself being this specialty fiber meeting as the end user. So I will focus much more not in many technical details of what we are currently doing, but as a user of specialty fibers, specifically turbine doped fibers. So the challenges that we face and how in some cases we can mitigate them on our sides, but we do not control the manufacturing of the fiber itself. So it's more a challenging presentation for the manufacturers that really make the fibers. So it will be a overall presentation mainly. So brief introduction on Amplitude. Amplitude is a worldwide manufacturer that you should know of ultrafast lasers since 2001. It addresses three main market segments: industry, science, and medical, with 4 manufacturing and R&D sites. So one in Paris, one in Bordeaux, which is the headquarters in Pessac, more specifically in Pessac. Another one in the US, in Milpitas, California, and the other one is in Porto, where I currently am. Overall, Amplitude have more than 450 employees, 5,000 square meters, including almost 2,000 square meters of clean rooms. And the main purpose is to design high power lasers for volume production. So the sites, since they address the manufacturing sites addressing industry and medical, they are certified with 9001 and 13485. Why is Amplitude in Portugal? So basically, it's a consequence of an acquisition that Amplitude made in 2022, where it acquired MW Technologies. So MW Technologies was a company that was founded in 2013 as a spin-off of another company called Photonics that was operating since 2004. So with this, Amplitude gained a new center in Maia, Portugal, that had a long expertise in this specific field of fiber lasers and also control electronics. So currently, we have some research and development for Amplitude, and as well, we complement manufacturing. Going more specifically to what is a bit of our work and also past work, I will focus on MOPA fiber lasers. And as you know, the fiber lasers, they started to gain traction, well, maybe 10, 15 years ago commercially, mainly because of the high optical efficiencies. So the advantages are very well known in terms also of thermal management, beam quality. The MOPA system also allows very flexibility operation, can be CW, pulsed. You can have different available wavelengths depending on the doped fiber that you use. And overall, from a practical point of view, they can be very compact, robust, low maintenance, and also reliable. The MOPA configuration is quite straightforward. Normally, you start with a master oscillator that provides you a very high control of if it's pulsed, of the pulse, that's the idea, and of the frequency of operation. And then you can have a sequence of amplifiers, fiber amplifiers, in this case, where the first one will provide the high gain. We call them preamplifiers, and the last one will provide you the high power that we normally call the booster. So basically, at the end, what we really want to know is what we really want to have is a very high power output that is given by the master oscillator. But the challenge is really to maintain this fidelity of the master oscillator, because we will face noise, gain dynamics, nonlinearities, dispersion, birefringence, so many effects that will distort the signal. And the main challenges normally that we face when we go to power scaling, well, first of all, it's the pump power limitations that are due to the finite brightness of the laser diodes that are normally available, or also on the doping concentration of the fiber core, of the gain fiber. Then we have other types of limitations, because when we have very high heat or intensity fields, they can induce damage to the fiber. So we can have fracture, melting of the core, thermal lensing, and we can also very easily burn the end facets of the fiber, especially if we don't have particular care with the cleanliness of the end facets, and also some photodarkening that it induces absorption because of the high intensity. The ones that we work a lot also are the nonlinear optical limitations. And in our specific case, not so much in some cases ultra fast, but we also were in the nanosecond regimes previously, where the stimulated Raman scattering. So basically, the laser signal, it's converted into forward frequency shifted frequencies. And if we just plot some of the equations that are given by this paper, we can easily see that once we try to have some more fiber length to have some more power at the output, because we do not have enough power with shorter lenses, then this starts to become the more limiting effect. Or if we have signals with a very small bandwidth, like single frequency seeders, we face sooner stimulated Brillouin scattering. And again, the main factor that is limiting the power scaling is SPS in this case. So how can we mitigate this type of nonlinear effects? So basically, we work a lot on different pumping schemes, backward and forwards. We can have different fiber designs from the manufacturers with different silica-based core geometries. We can have tapered fibers or photonic crystal fibers. We try always to go for the increase of the mode field diameter. The challenge here is to maintain the mode quality. Otherwise, we have to have some mode filtering mechanisms afterwards. Then we try to reduce the fiber length as much as possible. So we look for high pump absorption coefficients on the fibers. And then we use other parallel techniques like Adler signals, temperature gradients, etc., just to break the nonlinearities that appears to us. So nevertheless, we still have many differences in many commercial available fibers. So I just put here an example of some tests that we did some time ago. And we just picked 8 different fibers ready available from different manufacturers. And they are from 25 to 30 micron core sizes. We use them as a booster, so large mode area double clad fibers for a signal at 1064 nanometers pulsed. And we tried for each case to optimize the length or the configuration in order to extract the highest possible energy before reaching the limits that I showed before. So we see some differences, and what we try to do here, and we focused a lot on the stimulated Raman scattering in this case, and we split it, the wavelengths. So we had some bandpass filters that allowed us to discriminate the total energy and then the energy that was in the signal and the energy individually that was also in the Raman. And we have fibers for the same total energy that in some cases still present a lot of nonlinear effects. So most of the power is in the Raman wavelengths instead of being in the signal wavelengths. So this is just an example of some fibers that we have tested in the past. And in conclusion, this leads me to the request that we normally make to specialty fiber manufacturers. So as a laser manufacturer, we look for passive optical fibers for beam delivery. So I saw already a presentation from GLO, and I'm pretty sure you are in contact with Amplitude. And also the active fibers for the pulse amplification. So generically, we look for high peak power handling, high efficiency, good beam quality, photodarkening free, and preferably high compatibility with available optical components, because it's always a challenge to have these new and very, very high performance fibers, but then it makes it difficult to put it in production and be compatible in terms of splicing or multi-field adapting, etc., etc. So thank you very much. This was my presentation, and I'm now available for questions.
So thank you very much, Miguel. And we already have a question from John.
Hi, can you hear me?
Hi, yes.
Yeah. Thanks for that talk. How would you quantify in the commercial market, not in the research lab, how would you describe or quantify the ability to suppress nonlinear effects today, SRS and SPS? Can you put some numbers to that? Generally, people know how to suppress or increase the threshold by 3 dB, 5 dB. What's the state of the art in practice in the commercial market today? Thank you.
Yeah. So yeah, it's very hard to give you an exact number because we have a very wide range of circumstances where they can be triggered. But for example, from past experience, and only talking about silica fibers, we have managed to decrease more than 3 dBs in some cases for the same condition, just applying some different techniques.
Two dB, I heard you say.
More than 3 in some cases, yes.
More than 3. Okay. All right. Thank you.
Welcome.
Yeah. Well, another question from Jan.
Yes, thank you, Miguel, for the presentation. You mentioned at the end of your presentation that you can have a need for long lengths of passive fiber. Am I correct? Can you specify what is length and the application, if you can disclose a bit?
I cannot disclose. I think the best is to put you in contact with the right persons that are very close to you and that you should know as well.
Okay.
So
Thank you, Miguel.
I suggest that, yes.
Understand the message. No problem.
I think another question from Simona. Yes, Simona, please.
Yes, what kind of signal power you want to reach? So how many millijoules are you looking for, or nanojoules, or micro? So what do you want to reach with the fiber that you are asking for?
Yeah, it's normally the answer is as much as possible. So yeah, it's true, because we try to extract as much power as we can from any fiber system. And in some cases, we have to go then to the solid state amplification to increase even more the power. So we try to work as much as possible in the limits of what the fiber can give us in terms of energy. So, and then there is, of course, there is the limits. They differ a lot in terms of depending on the pulse width, depending on the intensity of the amplitude of the power, etc., etc. So I don't have an exact answer or a number. My answer is as much as possible, and then we try to extract from there.
Okay, thank you.
Is there any other question for Miguel? So I don't see any. So Miguel, as I asked to the other speakers, if you can put also your email address in the chat, then people can contact you afterwards for further discussion. And thank you very much for the presentation and for showing the needs from the point of view of the laser manufacturer.
Thank you.
Thank you very much. So we can continue the meeting, and our next speaker is Jan Stepanek. He's a R&D team leader and R&D laboratory manager of the company Fluence Technology. So Fluence Technology is also a laser manufacturer based in Poland, ultrafast laser manufacturer with different applications in material processing, bio applications as well. And he's going to present today all fiber ultra short pulse lasers with specialty fibers. So Jan, the floor is yours. Thank you for being here this afternoon.
Okay, hello everyone. Give me a sec. Okay, now the presentation is good.
Still loading in my computer. Now it's working. Thank you very much.
Okay, nice. Hello everyone. Thank you for having me. Thank you for this opportunity. I will also be giving a talk with similar approach as the previous speaker. So I will talk as an end user of the fibers, and I would like to inspire you what can be needed to push the boundaries. As it was said in the introduction, I am a team leader at Fluence Technology, mostly focused on all fiber, all PM fiber setups to deliver high energies. And the talk in general will be focused on all fiber ultra-short pulse laser with specialty fibers, and there will be a few slides about the special case of all fiber setup for 920 nanometers for biology. Okay, but firstly, a few slides about Fluence. So we are the laser manufacturer that was founded in 2016. So we have over a decade of delivering ultra-short pulse lasers. The technology is being developed since 2003 when it started on best Polish universities, and we provide high power industrial grade lasers for materials, microprocessing, research, and medicine. And we have two locations in Poland. One production factory is in Warsaw, and the second one is the ultrafast laser application laboratory in Wrocław, where we develop the micromachining processes. Okay, and now a little bit of overview of our products. So we have three main lines of products. The most powerful one, which is Jasper X1, with the average power over 60 watts and pulse energy over 200 microjoules. The second one, air-cool and compact Jasper Micro, with 7 watts of average power and 5 microjoules of pulse energy. And the third one is the heart of each of the lasers, so the oscillator, which gives 20 milliwatts of average power, 1 nanojoule of the pulse energy, so works at around 220 megahertz. So now I will do a follow-up to a presentation which Jacek Sobków, also a team lead at our company, gave some time ago. So what is the perfect fiber for us to work with and develop more energy, more peak power from the all fiber laser system? So firstly, large mode area, more than mode field diameter more than 15 microns. The few modes, the better. M squared, preferably would like to have 1.1. The second needed thing is high ion concentration, and here I have some numbers. So for ytterbium doped fibers, we are looking for core absorption over 3000 dBs per meter, and this corresponds to clad absorption over 30 dBs per meter. Of course, it depends on the overlap integral of the pump and the core, so the active fiber geometry. And here are also some things that we are looking for. So large core to clad size ratio, which increase the overlap of the pump and the doped core. And of course, we are looking for all polarization maintaining fibers. So the mechanical, the part of building the fiber setup is easier when we don't have to worry about changing the polarization state. and also some nonlinear effects which can be increased when we have two different polarization states inside of the fiber. And now I would like to talk a little bit about this 920 nanometers project. It was a challenge from our scientific client. So why it is important? 920 nanometer wavelength can be used in two-photon microscopy to observe live biology tissue. And why it is difficult? Because neodymium doped fibers have an emission peak around 1064 nanometers, and somehow you have to mitigate to work around 900 nanometers. And to do that, the solution that was proposed by the fiber manufacturers is to use special structure of the refractive index of the fiber. It is W-shape structure of the refractive index. When we have the highest refractive index in the core, then is the first clad with the lowest refractive index, and there is a second clad with the refractive index somewhere in between. And what this kind of structure gives us is the low pass edge filter for the longer wavelengths. So we increase losses for the longer wavelengths, and there is an cutoff wavelength for the LP01 mode in such fiber. This gives losses for this 1064 nanometers radiation, and this allows to work at 900 nanometers. We have used for this product commercially available neodymium doped fiber with 5 micrometer core and 80 micrometer cladding. So this overlap integral was optimized, but still the pump absorption for this fiber was maximum half of decibel per meter, which resulted in low gain efficiency, some problems with nonlinear effects. Yes, but still we managed to design and develop all fiber oscillator with this active fiber that works at 920 nanometer wavelength with repetition rate over 21 megahertz. It was all PM fibers, 920 central wavelength, and have self-starting passive mode locking. And with this oscillator, we then developed full all PM fiber amplifier that delivers the spectrum with the bandwidth over 20 nanometers at the 10 decibel loss level, which could be compressed below 200 femtosecond. The average power was above 1.5 watt, which resulted in energy over 70 nanojoules, because with this oscillator there was no changing the repetition rate, so it was over 21 megahertz. Setup gain efficiency was around 9%, and m squared below 115. Here is the beam, and in the right down corner you can see the real image registered with this setup, and the Biology Center Nensky in Poland, in Warsaw, and this is the live shot of the mouse brain during some activity registered with the two-photon microscopy setup built with our laser. So to sum up, what we can do and what we're looking for is to integrate in our setup fibers that can push boundaries, and it will be active fibers, passive fibers, of course, large mode area, PCF also, to make better products. And to be more specific, we are looking for highly doped, as high as possible, extremely large mode, so over 30 microns, preferably with the bending radius also reasonable. Less than 100 millimeter gives us possibility to keep the laser compact. M squared also below 1.2, but preferably 1.1. What is more, we are also looking for testing some fiber delivery for mostly two energy ranges, so 5 to 25 microjoules or over 200 microjoules. And what we are also looking for are custom active termination and connectors. And this is all I have prepared. Thank you very much for attention, and I am ready for questions.
So thank you very much, Jan. So again, we have time for questions from the audience. Is there any question to Jan? I could perhaps start with a question about your last sentence about the connectors. Is there something specific you are looking or something you are missing in the offering that are nowadays in the market?
What we're looking for is collaborations, and when we find this perfect active fiber, it is hard for us, for now at least, to make it industrial production of end caps and connector that will have good thermal properties. So if we have the new active fiber, that we have to somehow make a connector to make it compatible with standard optics elements. So we are looking for a cooperation in this area.
To develop like a specific interface between the components and the fiber.
Yeah.
Yeah, Omar, you have a question from your side?
Yeah, thank you, for the nice presentation. You mentioned that you have used a 5-micron core fiber with W type. Have you tried another? You said that you were limited by the nonlinear effects somehow. So have you tested other fibers, neodymium fibers, with other core diameters? So I'm saying that because Excel is providing small cores, but also some large core like 12 micron core and 20 micron core fibers.
Yes, in this project, as I think I can say this because these neodymium fibers have been using are formerly X-Blue fibers. Yes, so this was Excel fiber.
Exactly.
Yeah, but we have tried to use larger MFDs, this 2080 fiber, but in this specific project, and it was, I think, early stage of this fiber, if I recall correctly, I have some problems with mechanical stability of the splices. Yeah, that after recoating, the beam quality was not satisfactory for us. There were some mechanical issues with generating high order modes on the splice points.
So maybe we can contact. We can continue talking. I mean, after the meeting, we can take contact. Yeah, and see how can we support you to solve these issues.
Okay, thanks.
Thanks.
Good. Any other question for Jan? I have perhaps one final question because I remember talking with some of your colleagues about your proposal of the burst mode as an interesting possibility for to improve the efficiency of the laser processing processes of materials. Is this something that also affects the selection of the fiber? Having burst mode in the laser can change the fiber that you are implementing in your laser, or is just like a procedure that you can play with the fiber that you select for whole manufacturing the initial source?
I think burst mode is not critical for selecting the fiber, because if you are using a burst mode, you are lowering the single pulse energy. You are increasing the average power, but the single pulse energy will be lower when you have many pulses in the burst. So these critical things to push the limits to have high energy from the all fiber setup will not be limited by the burst mode, by the single pulse mode.
So it's not affecting like the construction using the fiber.
Yeah, the average power from the setup will be higher, so the thermal problems can be increased, but not the energy related problem or non-linearities.
Very good. Any other final question for Jan? So I don't see any hand. So I thank you again, Jan, for being this afternoon with us and for showing all these requests and how the EPIC members support you. So thank you very much for your presentation this afternoon.
Thank you very much for having me.
Thank you. So we can move now to our next speaker, So it's a pleasure to introduce Joachim Gericke. He's the product line manager at the company Photonics, also a well-known company working with specialty optical fibers, developing also bundles and assemblies of fibers. And he's going to present the broad spectra fiber solutions for high-performance laser applications. So Joachim, the floor is yours. Thank you for being here today.
Thank you. Yes, thank you for the introduction. I hope you can see my screen.
Not yet, not yet.
Not yet. Okay, check. Certainly now.
Now it's working. Thank you so much.
Super. Yeah, from UV vis to mid-IR, broad spectra fiber solutions for high-performance laser applications. This is the presentation for today from Photonics. Already at this point, I would like to take the opportunity to thank you, the EPIC team, for the organization, and also thank you to all the participants to follow on the thoughts we have on this subject. Following the guideline from EPIC, we have the following agenda for this short presentation. First, what do we offer at Photonics? What kind of fiber types do we have in our portfolio?
Joachim, we're still in the first slide, so we don't see the agenda yet.
Okay, hold on. No. So yeah. Now we have the agenda, sorry. So what do we offer? This is what is within the portfolio of Photonics in terms of fibers. Then what do we do? Here I'm going to talk about the unique optical fiber production of specific fibers. And finally, what we are looking for. And I will end up everything as usual with a summary and to be open for questions from your side, actually. The products of Photonics are separated in three main product groups. The first, the FlexiRay, concerning fibers, cables, bundles, and accessories. This is also the main topic of this presentation. Then the other product group concerns everything which is related to probes in terms of spectroscopy, accessories for these probes like couplers and so on. And finally, we have a product group called Flexi Services, which includes everything like loan and demo equipment, installations, training, repair, and also pretty important development work with some scientific organizations and universities. If it comes to the fiber product portfolio, Photonics is going to offer everything from the UV, here specific the silica fibers for UV to vis applications, but also silica fibers, of course, from vis to the NIR, followed by the chalcogenide fibers. In this presentation, I will mainly focus on our polycrystalline solutions and the hollow glass waveguide fibers in the mid-IR range. Talking about this, we will also have some fluoride fibers in our product portfolio and others. So we are not limited to these, but this is our, let's say, main field of business. If it comes to the polycrystalline silver halide fibers, this is something where I would like to point out that Photonics is the only company globally which can produce these kind of fibers also in a high volume scale. We have further developed the original innovation since the late 1990s for this high volume production, and we regard ourselves as the provider and supplier of polycrystalline fibers. The main applications, here you see some features, but the main applications are infrared pyrometer applications. We also have IR images which we can provide with. It's also applicable for laser delivery or power delivery of CO2 and CO lasers. And also laser coupling for QCL lasers. The second type of fibers which we are offering, which are specific for art photonics, are the so-called hollow glass waveguide fibers with an infrared range from 3 microns to 18 microns. Here, the unity is that we can have very low diverting radiation or light. We can incouple that, and we can also bring the light then and transport the light from one location to the other location. Here, actually, we are working with partners for the production, and we can also give a good inner diameter from 500 to 1000 microns for it. Usually these fibers are double polymer coated to provide a high flexibility and to provide them also with a certain strength. If it comes to harsh environment, the solution from us is definitely these so-called metal-coated fibers. Here we are going to coat silica fibers with either aluminum or with copper. These metal-coated fibers, they resist harsh environment, like not only high temperatures, up to 600 degrees with copper, but also very acid environment or nuclear radiation. The fibers itself, they are not outgassing, so to say, and they are very common or more and more coming in the medical applications. We are not, or we don't regard ourselves as a sole supplier of fibers. It's even more that we are a provider of so-called cables, so packing fibers with accessories. This is our strengths. I don't want to get to all these different applications here, but we could supply fibers for vacuum applications, an example with a feed through to the chamber, to the vacuum chamber. Very common are collimating or refocusing objectives for infrared fiber cables, connectors, and so forth. Fiber couplers also for lasers. I mentioned earlier the CO and CO2 lasers. And not to forget fiber couplers also for various detectors. Another strength of art photonics is the manufacturing, the design and the manufacturing of bundles. So taking single fibers and put them together in various arrangements and geometric. Here you see some application or some possibilities. These circular fiber arrangements. Here we have a linear arrangement with a very dense packing of fibers. This is a very specific arrangement where we combine various different fiber materials. So it could be polycrystalline fibers with silica fibers in one bundle to provide specific parameters and performances. Here we have a rectangular example for imaging, an example. Yeah, with whom are we going to cooperate? We are looking for partners in various industries. Yeah, I name here some of these industries we are already cooperating with, mainly the medical device industry, life science, pharma. Pharma is becoming more and more important due to these process analytical technologies. Food and beverages, chemical, aviation and space, petrochemical, of course, defense and other industries. And the application for these industries, specific on these industries, could be, of course, in laboratory, in the research and development departments, but also in productions. And we also act as a OEM supplier if it comes, an example, to probes for spectroscopy or for laser delivery cables in certain for certain applications. Yeah, whenever it comes to a solution for broad spectral fiber technologies, due to the fact that Art Photonics has the knowledge and the decades of experience in packing fibers and to make out of a fiber cables, I think that we are the right partner. If you have specific requirements, applications, or if you need for a specific solution, then we can provide you with it. Actually, we are located in Berlin, founded in 1998. As I said, we provide fibers in total from 180 nanometers up to 18 microns. We are specialized in these so-called peer fibers, these polycrystalline infrared fibers, but as I said, also mentioned the hollow wave guide lights and metal-coated fibers. If you have further questions, we would be more than happy to be your partner and answer also questions. Thank you.
Thank you very much, Joachim. So again, we have time for questions or comments. I can perhaps start with a question about the potential application of your IR fibers in lasers applications. How do you see the potential of this market? We see some laser sources going in this direction of mid-infrared wavelengths. What's your point of view from our photonic side?
So especially the polycrystalline infrared fibers, they are very suitable to deliver power from the laser source, an example from the CO2 laser, to the kind of the application itself. Instead of the articulated arm with mirrors and so on, we can substitute this with our fibers. Another application is, I mentioned that, in spectroscopy, more and more spectroscopic applications are also in the range of mid-IR. And here we offer probes, but also with our polycrystalline fibers inside to send out the light and to receive the light for the analytics.
And regarding the metal-coated fibers, do you also explore other kind of metals for other applications? I think perhaps in gold and other type of metals, or for the moment with aluminum and copper?
Yeah, especially aluminum and copper, also to the heat restriction. Copper is very suitable, in example, to be applied with or to work in very warm and high temperature environment. And of course also aluminum for very specific chemical environments where steel or other metals would not be suitable. Yeah. But in theory, every kind of metal is thinkable, but it turned out so far in the market that there is a specific demand for aluminum and for copper. Yeah.
Yeah. I don't know if there is any other question for Joachim. So I don't see any hands. So again, Joachim, if you can use the chat to put your email address, and people can contact you afterwards for discussion. So thank you.
More than happy. Thank you.
Yeah. Thank you for being here this afternoon and for the presentation. And we can now move then to our final speaker today. So we have Omar Sani. He's the product line manager of active fibers at the company Excel. So we talked already a little bit about active fibers, and Excel, quite well-known company, developing different kind of products, being fibers one of them. And he's going to talk about the rare earth doped fibers for fiber lasers and amplifiers. So Omar, the floor is yours. I already see your slide.
Okay.
So yeah, you can proceed.
Yeah.
Thank you for being here.
Yeah. Okay. Can you see my screen now?
Yeah, we see the screen. We hear you well.
Okay. Okay. So, okay. Okay. So, good afternoon, everyone. So, my name is Omar Sani, product line manager of active fibers for lasers and amplifiers at Excel. Thank you, Antonio, for the introduction, and to the whole EPIC team for the organization for this meeting. Today, I will give you an overview of our rare earth doped fiber portfolio, covering application from 9xx nanometers up to 2 microns, of course, for fiber lasers and amplifiers, including terrestrial and defense and space environments. So let me start just first with a quick overview of Excel company. So Excel is a global high technology group with more than 2,000 employees up to date, and over 370 million euros in revenue. A key point for us is that around 20% of our turnover is reinvested in R&D, which is crucial and critical for advanced photonics and fiber technology. We also operate globally with more than 75% of revenue outside of France. So we support our customers worldwide with a strong industrial footprint, as you can see from this slide, and 24/7 technical support, which is especially important for all the laser system integrators and long-term programs that we collaborate. So our technology is supported by 2 joint research laboratories here, one in Saint-Étienne and one in Talence, and more than 20 industrial sites, allowing us to combine the research level innovation with industrial scale manufacturing. So to just describe the general activities of Excel, so Excel operates across several high-end markets, such as aerospace, robotics, navigation, and photonics. And for this meeting, we will focus on photonics. So next step is to show you what's Excel activities in photonics. So within photonics, we not cover only the specialty fiber, but we also cover other activities, lithium niobate electro-optical modulators, micro-optical assemblies here, and complete laser systems, especially for quantum applications and high performance applications. So the system here level vision is important for us because when designing active fibers, we really need to know that these fibers really work in real laser architectures. So now if we focus a little bit on the specialty fiber, so here the activities is three activities. So Excel has 3 main activities: passive fibers for harsh environment here on the left. We do also have polarization maintenance spoon fibers activities on the middle, and we have rare earth doped active fibers. So on this meeting, I will focus on active fibers. So for active fibers, we cover amplification from 9xx nanometer range up to 2.2 microns with neodymium, ytterbium, erbium, ytterbium, codopin, thulium, holmium, and thulium-holmium codopin dopants. So we offer also different geometries, so single, double, triple clad designs, single mode to LMA, and PM and non-PM features. So for both terrestrial and space grade applications. So what I will do next is I will just scan the full spectrum of the wavelength by rare earth, and I will focus on each highlight references. So let's go through the main wavelength region now. So I will start with the neodymium doped fibers for 9xx nanometer amplifications and lasers. So Excel provide neodymium fiber solutions. So amplifications around 9xx nanometers here, more precisely, let's say 910 nanometer to 930 nanometers is challenging because of the strong competition with the 1060 nanometer transition. So Excel will address this with tailored refractive index profile and fiber geometries. We provide here, we provide a large offer and complete offer of neodymium doped platform suitable for CW, QCW, and ultrafast regimes. So this offer can go for single clad fibers like here, it is written here. So for DFB lasers, DFB fiber lasers, and pre-amplifier stages where we don't need, we need more high gain than more power. And we do also have we complete the offer with the double clad fiber solutions, delivering from hundreds of milliwatts to hundreds of watts. So the application, the main application and collaboration that we have with customers for these fibers is in the application of medical imaging for multiphoton microscopy and frequency conversion, deep blue and deep UV. So moving now to the second rare earth, which is ytterbium for fiber lasers around 1 micron. So here, ytterbium doped fibers, Excel work on ytterbium doped fibers for a long time. Ytterbium doped fibers are really the backbone today, and we can see it for high power fiber lasers systems. So at Excel, we cover the whole range from very low noise single clad fibers for seeders and amplifiers, same spirit and same mindset that for the neodymium. And we also offer double clad fibers designed for high power amplifications. One point that is increasingly important for many of our customers that we can feel during the 1 or 2 years ago is that Excel is fully European manufacturer. So the fiber design and the manufacturing and qualification are all done in Europe. So for the sovereignty driving programs, especially in defense, this means supply chain control and long-term availability. So in terms of performances, I would like to seize this opportunity to put just the focus on one work we're still continuing is on our 20 micron core 400 clad fiber that we have started 2 or 3 years ago working on this design to achieve kilowatt and to address kilowatt fiber systems. So in terms of performances, this fiber today have been demonstrated to achieve more than 2 kilowatt output power in CW regime with very stable operation and no TMI transfer mode instability observed. So in fact, the performances was limited here by the pump budget, which was limited. So this make our ytterbium doped fibers very robust solution for industrial lasers, for industry, or can be also and driven by the defense and the directed energy systems. So just to take the opportunity also to say that when we are dealing with kilowatt output power levels, the matching is very important. So in addition to active fibers, we provide matching passive fibers and high power fiber gratings. So the passive fiber is double clad and single clad, and the FPGs are designed also for kilowatt class operation with optimized thermal behavior to simplify the integration into the high power laser cavities. So again, all those components are manufactured in France, ensuring EU origin and supply chain control. So let me move to the next slide. Will be on the 1.5 micron wavelength range. So here I will just briefly describe erbium and erbium-ytterbium doped fibers portfolio of XL. So at 1 micron 5, XL has built a very strong and long-standing expertise in erbium and erbium-ytterbium doped fibers. So over the years, we have developed more than, if I summarize like this, more than 50 references with a clear focus on efficiency, long-term stability. Here I'm talking about photodarkening-free core compositions and system-level performances. So our erbium and erbium doped fiber are designed with erbium-ytterbium doped fibers are designed with low parasitic emission, which is one of the main limitations in the code open, and photodarkening free, as I said, and high efficiency, which makes them extremely robust for demanding applications such as optical ground base station, where the power high power is required more and more. Generally today, we have requests of more than 20-30 watt output powers for quantum applications as well, and medical cavities for applications in medical, like such as skin treatment. Okay. So here, what I want to focus before moving to the next slide is that in 2025 we introduced a new 10130 erbium-ytterbium doped fiber called SMX fiber. SMX standing for single mode extended power, which has now been qualified and demonstrated up to 30 watt output power with maintaining a diffraction limited beam quality. Here maybe it's a little bit too small to see, but we're around 0.3 and below 1.1 m square. And as we can see here on this graph, this fibers show very high rejection ratio between the 1.5 and the 1 micron parasitic emission, here more than 40 dB. And what is also have been worked in this design is the long-term reliability, because it's not only important to have the efficiency, the beam quality, and the low 1 micron emission, but reliability is important also. So here, just a graph to show you, we have run this fiber at 30 watt output power for more than 700 hours without any degradation. So those results have been already, let's say, presented at Photonics West 2026. So finally, I will briefly cover our 2 micron also fiber solutions, which are so at 2 micron here, let's say XL has built a very strong and solid experience for 2 micron active fibers. Here, the 2 micron we are working for many years, more than 15 years, on different custom projects that give us now this strength to master all the dopants that can emit at 2 micron. So here, mainly the thulium, the holmium, and also the co-doping of thulium and holmium. So in this slide, I'm showing just a couple of also representative scientific publication but they are only examples of much broader body of work, but they illustrate that our fibers have been used in multiple experimental work and scientific demonstrations showing strong performances in terms of output power and also efficiency across the 2-micron wavelength range. So this accumulated experience give us a very good understanding today of the specific challenge of 2-micron fiber lasers and amplifiers in terms of power scaling, efficiency, and system trade-offs. So as a result, we are able to propose today solutions that are already aligned with realistic laser architectures, not just isolated labs results. So also, as I said, for the 1-micron, for the 2-micron, we also provide matching passive fibers and also massive passive matching components such as FBGs and narrow line width DFB seats. So an important differentiator for XL now is the radiation hardened active fibers, where I will dedicate the last minute. So here we have more than, I would just want to recall that we have, more than 20 years of experience in radiation hardened fibers, here developed through ESA and CNES programs. So XL is a pioneer in rad-hard erbium, ytterbium, and erbium-ytterbium doped fibers for optical free space communication with an extensive in-flight heritage that we can mention here. More than 6 million flight hours accumulated, and for different missions going from LEO to GEO to deep space. So. And here we offer also qualified on-shelf products with guaranteed radiation-induced gain variation up to TRL9. So here we can say that XL also is the only manufacturer that specify those parameters relevant to space environments, which are the RIA, so the radiation-induced attenuation, and the radiation-induced gain variations. So this is qualified from batch to batch on all our rad-hard fibers. So to conclude, just want to say that XL provides comprehensive and extensive portfolio of rare earth doped fibers covering wavelengths from 9xx to 2-micron for different application, going from terrestrial earth application, defense, and space application. So what I would like to say also is that beyond the catalog of the products that we have, we are also able to develop custom active fibers tailored for specific system requirements. And more broadly, XL can support complete laser architectures, providing not only the fibers, but also the fiber Bragg gratings, mirrors, the modulators, the narrow line with seeders. So if you are looking for a long-term partner rather than just fiber supplier, XL is ready to support your project. And thank you very much for your attention. Thank you.
Thank you very much, Omar. So we have a few more minutes for questions for Omar. Yeah, John, please.
Hi, thanks for that talk.
Thank you.
I'd like to ask you and all of the rare earth doped fiber manufacturers that we've heard from, to what extent has this industry been impacted by changes in China export policy of rare earths?
Okay, so you mean so regarding we are not, I would say we are not affected in terms of active fibers, because today our customers is really distributed around the world. So we are not dependent on one market, on one country. So we are not really affected by this, I would say.
I'm sorry, I didn't make myself clear. I don't mean China as a market that you sell to. I mean your ability to procure rare earth materials, raw materials. Have you or do you, or this market, this industry generally been affected? Really, a lot of what we hear about rare earths is mostly cerium and neodymium. But has the rare earth doped laser industry been affected by what's going on with China? Their willingness to export.
So okay, so now thank you for the question again. So I am not on this side, so I will not have a clear answer. But from where I am, what I see is that we are not really affected for this supplying. I mean, rare earth elements, because I think, I mean, we do have many suppliers. Yeah, I mean, different suppliers, not only China. We know that there are other suppliers. So from now, I didn't hear any problems of rare earth, and even for sure sometimes we need to take some cautions and be careful when there's some things happening like this. So we don't have only one supplier, but we have multiple suppliers in order to have other plans. Thank you.
Thanks. Okay, thanks.
Yeah, thank you.
Thank you very much, John. Any other question for Omar? Yeah, Robert, please.
Okay, thanks for the talk, Omar. Can you comment on the multi-phonon absorption of silica on the 2-micron emission for thulium, holmium, and the thulium-holmium system?
Okay, so we are meaning here in the background losses in silica at 2 micron and beyond, right? Yeah, okay. So here our fibers, we are working on especially on the 2 micron fibers, thulium and holmium, to minimize during our process the OH content, in order to minimize this multi-photon absorption. So we have a careful process for those, specifically for those fibers, because we know that the absorption, the background losses can increase above 2 micron, and we control that very, very tightly.
Okay, thanks.
It's okay, Robert? Okay, so we can move to Jan's question.
Thank you very much for the talk. Do you hear me?
Yeah,
Yeah.
we can go, Jan.
Okay. Yeah, my question or the comment maybe is more general, because the picture I have seen is that mostly you are focused on continuous work laser with the AFGs and the narrowband pass filters. And the comment I have, and correct me if I'm wrong, is that for the continuous work lasers, you are not that much concern about low ion concentration and low power absorption, because you can amplify radiation in the long length of fibers. And it's also a positive aspect for you, because then thermal management is easier if you have the long fiber. And from the ultra short pulse point of view, where I am standing, I would like to have the highest possible ion concentration, to have the shortest possible fiber, as long as I can not damage it thermally. Yeah. So what about of your offer in this area?
Okay, so we are talking about neodymium, right?
Neodymium, ytterbium.
Okay. So for neodymium, I pointed the CW, the continuous wave, but our fibers works also in ultrafast. We have a control we have highly doped versions that is not I didn't show on the presentation, but in neodymium doped fibers, for example, I'm not talking about the 5 micron or the 12 micron, but we have released recently the 20 micron core 100 clad, which is this first reference is medium doped, and we are working, we are progressing on and would like to release in the future, in the current year, highly doped 20 micron core neodymium fibers to specifically address this ultra-fast market at 920 nanometer, because we know that it is important for some customers to achieve the 1 microjoule output power after compression at femtosecond pulse widths. So this is for the neodymium. For the ytterbium, we do have all our fibers, let's say double clad fiber. In single clad, we do have highly dopant concentrations. As I mentioned in the slides on ytterbium, I can reshow it again. So in single clad fibers, we do have some highly doped and medium doped concentrations. And for the double clad, we are working to reach the maximum of the doping concentration by monitoring also the clustering. But I mean, we know that, yeah, for pulse application, the clustering is not that much important because the gain that you want to achieve is not too high. So you can accept a fiber with a little bit clustering, but highly doped. But this we do have some fibers that I didn't show here, but we can exchange by email to check to see your request in terms of absorption. What are you looking for example, at which pump wavelength and in which geometry. So this can be something that we can discuss further by email. I can send you an email to continue this exchange.
Okay, so we'll be in touch.
Yeah. Thanks.
Thank you very much.
Thank you very much. Thank you.
Thank you very much, Jan. Any final questions for Omar? So I don't see any other hands, so it's 5 p.m. as well. So I think we can close the meeting for today. So here you have the poll. It will be great if you can answer and let us know your thoughts about the meeting today and give ideas also to improve for the future. So thank you to everybody for answering the poll and give us your background and your ideas for the future. Just sharing finally my screen to remind you the meetings that we will have in the future, the meeting that we will have at Amplitude, and the meeting that we will have at Airbus facilities. So remember, November, we will talk about laser processing of materials. So I'm sure that for most of you could be an interesting topic, talking about ultrafast laser, but also about components, about specific solutions to develop laser sources that will be used in microprocessing applications. And then the meeting we will have in Airbus about fiber sensing, where we will discuss about the sensing itself with ideas for aerospace, but also about the fiber preparation solutions and other related components, metrology tools, and so on. So take note of these dates: Airbus in May, Amplitude in November, and I hope we can see you there. And thank you again for being here. Thank you to all the speakers today. It was a nice discussion. Thank you to Simona, Jan, Samir, Miguel, Jan, Joachim, and Omar for the time for preparing the presentation and for the discussions. And I hope to see you in a future EPIC event. Thank you and good afternoon, everybody.
Thank you very much. Have a nice
Thank
day.
you very much.
Thank you.
Thank you, everybody.
Thank you very
Thank you.
much. Bye.
Good
Bye.
afternoon,
Bye.
evening. Bye-bye. See you soon.